welcoming Dr. Aran Emini from LIUM, France, who will be speaking on low-resource speech processing in current paradigm of AI.
Hello, everyone. I don't know if we should stay to wait for people to come back or start. Thanks for inviting me for this valuable event. I want to say a special thanks to Dr. Shayan for inviting me, for Dr. Daud Atrushi. The title of my presentation is Low-Resource Speech Processing in the Current Paradigm of Artificial Intelligence. In the title of my presentation, I have three keywords that, by explaining them, I hope to give the context about what we means by low-resource speech processing in the current paradigm of artificial intelligence. Firstly, I want to talk about speech processing. What is low-resource language? And finally, what I mean by the current paradigm of artificial intelligence. From the early days of AI, creating tools to communicate by means of speech with machines was a dream for computer scientists. To transcribe the speech, to generate the speech, to interpret the speech, to extract information from the speech. That's the objective of speech technology or speech processing. The main areas of speech processing here, you can see the automatic speech recognition, ASR, which for us, we call it the core technology of speech processing because it can lead to many more technologies. We have text-to-speech, how to generate the natural speech from a written modality. Spoken language understanding, how to extract information from the spoken dialogues. Speaker recognition, the authentication of human identity from their speech utterances. And recently, multimodal interaction by a mixture of speech technology and LLMs. Low-resource languages, as you know, we have about 7,000 or more than 7,000 languages around the world. Unfortunately, we have speech technologies for about 100 languages and varieties, or 140, 50. That's the maximum, the functional systems that, for example, are operating now for speech recognition. And from these 150 languages, most of them comes from different varieties. For example, we count 10 dialects of Arabic or several dialects of English. And for the rest of languages, we don't have functional systems. What is the obstacle that we cannot develop functional practical systems for other languages? The first obstacle is having annotated data into modalities, I mean, in the speech format or text format. The languages with a smaller number of speakers are not so interesting for researchers, for commercial companies to be explored. Also, we need many basic tools such as tokenizers, parsers, etc. that we don't have for these basic tools for low-resource languages. But we should not leave these languages alone because we want to preserve the languages. We want to be inclusive. We want to develop these technologies not just for few number of languages. The objective is to include the majority of humanities and cultures. Here I want to start my presentation by this question. Imagine you are a speech engineer. You have your boat is sinking. You have 2 hard disks at your hand. In one of them, you have just 10 hours of annotated speech, and in the second one, you have 1,000 hours of raw audio. But you can save just one of these 2 hard disks. What's your decision? You decide to save which one? Maybe this question, the answer to this question is different from the answer 20 years ago. That's why I'm talking about the paradigm, the shift paradigms of artificial intelligence. Here, we have the 4 main stages of artificial intelligence. We started by encoding the knowledge in terms of some rules in expert systems. We have the classical machine learning algorithms. The classical machine algorithm try to resolve the problem of encoding knowledge in terms of knowledge base by making some feature engineering. The next paradigm is deep learning. In deep learning paradigm, we try to resolve the problem of feature engineering by extracting the features automatically in compact and hierarchical representations. And finally, in recent years, in general intelligence, by having the LLMs, we can have more richer representations, and the general intelligence try to resolve another problem, the problem of having a custom model for a specific task. In each paradigm of artificial intelligence, we encode the linguistic information in a different form. For example, if we have the word of duhok, in expert systems, we were just encoding in the format of a text, and we were applying some logical engines on it. In the classical machine learning, we were representing this word in terms of 1 decimal number, for example, or a binary number. In deep learning, we have a static vector that tries to encode all related information that is related to duhok. And recently, in the LLMs, we have a dynamic representation for this word. For example, when we talk about politics, we have a specific representation for duhok. When we talk about science, we change our representation a little more. And having these representations, we can develop a general system instead of having a custom technology for each task. In the domain of speech processing specifically, we have self-supervised learning. Here, the idea is to learn from the raw audio. Maybe we have the partial answer to my question here. The idea here is to learn from the raw audio without having annotation. The idea comes from for example, when we have a child, the child doesn't learn everything by telling them that's the meaning of this word, try to make the sentences in this way. The child tries to explore and learn by themselves to have a contextual information about the language. In this configuration is the most known architecture for developing technologies such as automatic speech recognition and speech translation. We have an upstream model. The upstream model is the self-supervised learning model. In this, the upper one, the model here tries to learn from the raw audio without having annotated data. At the end, we have a small number of parameters that are, for example, related to a low-resource language. But the upstream model can be trained on all languages. For example, we can train a model on English, and we can transfer this information, this knowledge that is learned by the model to another language, for example, to Kurdish. The main type of supervised learnings that are used a lot in speech processing are contrastive representation. Here we define at each mini batch, for example, when we give some examples, we have positive and negative examples. We try to reduce the distance between the positive examples, and the objective is to increase the distance between the negative, between the positive and negative examples. Wave-to-vec is the most known and used architecture in self-supervised learning. Here we take the speech signal. We have a latent space. In the latent space, we create a copy for our latent representation. And from this, the second copy, we apply a mask. I mean, for example, we put 0 for some parts of our representation. And at the end, by the contrastive loss, we try to predict the missed part of our information. Having this model, for example, we can take the output of the self-supervised model and use it for speech recognition, speech translation, and for speaker recognition. Another known self-supervised learning is wave-to-vec BERT. This model has been modified to not just capture the low-level features of audio, but higher level, I mean semantic level of information. By replacing the transformer with conformers, we can capture a longer context and have a more richer representation in terms of semantic. That's why this model is mainly used for speech translation. Here, Seamless is a very successful project from Meta. Recently, they published this model in Nature. The model is multimodal. We have an encoder for the text and another one for the speech. In this system, they use wave-to-vec BERT because the main objective of this system is speech translation. I present these models because I used them for Kurdish language, and because of that, I am presenting them to show how we use these models. Whisper is another successful project by OpenAI. Here we have weakly supervised learning. The Whisper model trained this model is not trained from the raw audio, but it's trained from annotated audio for speech translation, for speech recognition, for speaker recognition. The system is multitask, but they receive the data from high-resource languages. At the end, by removing the last part or by extending the last layer of our model, we can simply modify it to low-resource languages. In fact, self-supervised learning resolves the problem of data limitation for low-resource languages to a high degree. For example, in the traditional speech recognition system, we needed 1,000 hours of annotated audio to have a robust system. But now, just by having 100 hours or less than that, we can have a practical system for a low-resource language. In the recent years, from 2020 and 2023, we are moving towards speech LLMs. In the previous work, always we had different downstream tasks. For example, we had a self-supervised model, but as the downstream task, we had speech recognition, text-to-speech, etc. But the objective here is to have a general model for all tasks that are related to speech. Here we have the main configuration of speech LLMs. We have the first block is similar to self-supervised learning encoders for speech. We have a fusion block, and at the end we have the LLM model. Here the idea is to connect the SSL models developed for speech and LLMs that are already developed for the textual mode. Here, for example, we have two modalities as the input. We have audio input, we have text input, and by having the fusion part, we can use the potential of LLMs and have a general model for all tasks that are related to speech. For example, the present models like such as ChatGPT, you can ask them just simply by speech, please transcribe this sentence for me. Please translate this sentence for me. Please tell me which subdialect of Arabic or Kurdish now I am speaking, and so on. That's the idea, to have a general system for all tasks that are related to speech. By having speech LLMs, we can resolve the model customization limitations. We can have a general system for all tasks. But unfortunately, because the LLMs need a large amount of textual data, it's not easy to fine-tune or to use them for low-resource languages. As I discussed, we can solve the part of speech encoder by having the audio for high-resource languages, but here the obstacle is having a large amount of text for low-resource languages. Having this background of the state-of-the-art of speech processing, I want to present some work that we had done for Kurdish, for two main dialects of Kurdish, Central Kurdish and Northern Kurdish. Here we have the map of Kurdish language. In Kurdish, we have many categorization and classification of dialects. Another problem for low-resource languages is having different varieties, having different dialects. Zazaki is, and Kurmanji from northern part of Kurdistan. In southern part of Kurdistan, we have Northern Kurdish, we have Haurami, we have Central Kurdish, and in small part, we have Southern Kurdish. It's the same for eastern part of Kurdistan. We focused on the green one and the yellow one, the two main dialects of Kurdish language that are mostly spoken. For me, working on low-resource languages is not just to do a research. In fact, I have two main principles when I work on low-resource languages. For me, it doesn't matter if you just publish a paper or two papers on a language. The low-resource communities need functional systems. They need a system to do dictation. They need a system to generate their speech. And the second principle for me is accessible. You can have very good system in your laboratory, but if you cannot make it accessible, it's nothing. If people cannot use it, it doesn't matter. Having these two principles and the limitations for Kurdish language, we had done this work. For Kurdish language, we have the lack of linguistic resources. We have the lack of financial resources. We have the lack of computational resources. For high-resource languages, we can translate the financial resources and computational resources, but for many low-resource languages, in fact, it's not possible to do that. In speech processing, the SSL models can resolve the problem of linguistic resource to a high degree, but they impose a new problem. These models are very big, and they are computationally expensive, and it's not affordable for many low-resource languages. Here, we took several strategies to resolve these challenges. Firstly, to address the linguistic resource, we do phonetic modeling. Again, for linguistic and computational resources, we worked on pseudo-labeling, and by knowledge distillation, we try to resolve the problem of computational resources for Kurdish language. Here we propose this architecture. At the left side, we have a small gold annotated data. We have the largest encoder, decoder, speech recognition, and speech translation models, the seamless. And we have a speech segmenter, and the input of the speech segmenter is a big raw audio data set. Having this large model, which is tuned or partially fine-tuned for Kurdish language, we generated a large amount of pseudo-labeled data, and we filter it. At the end, we use this data to train a lightweight model, but the objective here is to preserve the same performance as we had with our large model. For phonetic modeling, this work is done on Central Kurdish. We collected a big text corpus from news agencies, from the web. We extracted the distribution of phonemes and diaphones of Kurdish language. We generated a sentence pool to have the same distribution, to have the same frequency of diaphones, to have the same frequency of phonemes. We don't care a lot about the semantic of these sentences because our target is phonetic level. The sentences are somehow meaningless. For some sentences, we have, for example, for 2 or 3 sentences, we try to have all phonemes just in one sentence. It's clear that the sentence becomes meaningless having this constraint. We use these sentences to collect a gold data set for Central Kurdish. Here, the AstroSoft corpus version 1 is the sentences, the data sets recorded from these sentences. We have also Common Voice, which is an open source recorded by people. We have more than 100 hours. That's our human annotated data set. And at the same time, we collected a large raw audio data set for Central Kurdish, more than 4,000 hours of raw audio, clean audio from audiobooks that are already published on web. Having this raw audio and the large model that we already trained, we generated about 2 million utterances for Central Kurdish. We have about more than 22 million words or tokens. This pseudo-label data is filtered using different metrics. For example, having the confidence that our big model gave to us. If the model is confident about the prediction, we hold these phrases. If no, we discard them. In some cases, our model goes into a prediction loop. We found these problems, and we discard the data in these cases. Here we have the results for our large model. The metric is known word error rate for speech recognition. The second row is the results that we generated by this, we arrived by this model on 2 data sets. In fact, the results are very close to high-resource languages. Having these results for our large model, we try to reproduce the same performance with a smaller model. The size of our small model is about 75 times lesser than the large model. Firstly, we tried our model with human annotated data. Here you have the results. The first one is the percentage of errors at the character level. The second one is at the word level. The first row is for human annotated data. In the second row, we have the pseudo-label data, the data that has been generated by the large model to train the smaller model. And at the end, we fine-tuned again the smaller model by our human annotated data to still improve the results. This data set is a very difficult data set. FLIRS, in fact, for speech recognition, we have many out-of-domain data. Here we repeated the same experiments on another test set. This one is more related to our context. We don't have many foreign words. Here you can see that the errors is about 1% at the character level, and at the word level, we achieved 7%. It's interesting that we can see here that the performance of our smaller model is even a little better than our large model. In some experiments, we look to find a trade-off between the size of model and the performance of our the performance. We reduced the number of trainable parameters to 15 million. Still, we have fairly good results. This model, for example, can be installed on mobile phones without a problem. But we choose the model with 30 million parameters as main model. For example, here we have a comparison between the resources that are needed for inference, having these two models. The lightweight model with 30 million parameters and the large model with 2.3 billion parameters. The results are same, or in some cases they are better. With one GPU, we can transcribe more than 1 hour of data, audio data in 4 seconds, but the large model takes 75 seconds. Here we have the same experiment for 3 hours of speech data. We extended this work for speech translation in Central Kurdish, but the previous work, we did somehow the same thing for Northern Kurdish, but we changed the type of the large models. We could to have good results for Northern Kurdish also. We have no practical system for Northern Kurdish following this approach. We extended our approach for speech-to-text translation. Here we added another model, a machine translation, a speech recognition, and a speech segmenter. We mixed these three models to generate a pseudo-label data, a triplet. For example, we have an audio utterance, we have the Kurdish transcription, and its English translation. At the end, we use this data set to train the end-to-end speech-to-text translation model. But before doing a transcription and translation, we try to improve the performance of speech recognition and speech and text translation. Here we have a big data set for Central Kurdish text-to-text translation. This data set collected from different projects in our previous work. Here we have the results for text translation. For example, for English to Central Kurdish, our model outperformed the Google and the NLLB from Facebook. For the CKB to English, Central Kurdish to English, the results are very close to the state of the art. Having this pseudo-label data, we could train different transformer models for Central Kurdish. For researchers in this domain, they know that having this metric, a blue metric, the higher one is better. It's really not easy to reproduce these results for a low-resource language. For example, the blue metric for Kurdish is about 20, 22 in the right side. But for high-resource languages such as English and French, we have 30. For between Arabic and English, the metric is about 24, something like that. By following this approach, we could resolve the linguistic resources for two main tests, for speech recognition, for speech translation. And also our objective was to reduce the computational cost. We reduced the computational cost.
languages, for example, other dialects of Kurdish. We have, for example, Assyrian in this region. It can be applied to other low-resource languages. From this work, we developed a platform for Kurdish language technologies here.
Raj, thank you very much, Dr. Aran, for the presentation and for the research you did. I'm just asking about the LLM model you used. Have you taken a baby LLM and developed or used the one standard one?
Sorry, your voice is not clear.
All right. Can you hear me now?
Yeah.
All right. I'm just asking about the LLM model you use. First of all, have you started from train it from scratch? So it's a baby LLM, or you use an existing one such as Llama or one of the open source? Because you mentioned that.
Yeah.
But I would like to know what is your plan on that, please. The second question, it's about, I couldn't recognize the size of the team. Is that a solo effort from your side, or you have a team over there in France? Thank you very much.
Thanks for your question. In fact, for this research, I just mentioned the LLMs to say the current state of research in this domain. But in our work, we use the traditional models such as encoder decoders for both speech recognition, speech translation, and machine translation. In this work, we didn't use LLMs because, as I mentioned, LLMs are not so efficient at the moment for low-resource languages. For Central Kurdish, we are in better situation in comparison to other dialects. We can apply it, but in our work, we used encoder-decoder architectures, transformers, conformers, etc. And about the size of the team, this work is done in the framework of a project in our laboratory. I was the main researcher in this group, but the size of our team, we are about 4 or 5 researchers. That's just part of our work that we had done. We have many languages in this project, such as Tunisian Arabic, such as Tamashek is a part of Amazigh language in Northern Africa, and Kurdish is one of them. We are 4 or 5 researchers worked on this project.
First, I would like to thank you for this interesting...
Sorry, your voice is not so clear.
First, I would like to thank you for this interesting keynote talk. I just have one question. It's about lightweight. Have you considered metrics for lightweight model like energy consumption or CPU processing, any processing cost?
Yeah, thanks for your question. In fact, I put the computational and financial resources separately because for high resource languages, you can translate them. If you have money, you can buy GPU. But ecologically, it's not efficient to do that. Many researchers, even for high resource languages, prefer to work on a smaller model and reduce the size of the model. We didn't calculate the energy consumption and the CO2 production, but as I showed, we calculated the inference time for having a 5 or 6 core of CPUs and 1 GPU. And it was clear, for example, with the large model, it's not practical to do an inference in real time having CPUs, but with the smaller model, the models now are available, and about 2,000 or 3,000 people are using them daily on the framework that I mentioned here. But we didn't calculate the energy consumption. It's clear that it's much lower in comparison to large models.
Yes, thank you. So maybe I gave the last question if there is no more questions. Okay. So can we consider the steps or the work you have done in your project that a kind of protection to the Kurdish as a language, I mean, and the roots of the language. Also, I know that you will start to work with other dialects. So to what extent these type of projects are going to protect the language by itself, or protecting as a result the nation? I mean, by digitizing the language.
The main objective of low-resource speech processing and language processing is the point that you mentioned, preserving the language, preserving the culture, not just for Kurdish, for all languages around the world. For example, we have the same mentality that we are doing research on low-resource languages, and there are some initiatives that targeted many more languages, especially in Meta. They targeted about 1,000 languages for speech recognition. Still, we are far from having a robust system for 1,000 languages, but that's the target, and one objective is preserving the culture. Not just, we started already by considering the main dialects that has more speakers, Northern Kurdish and Central Kurdish, but our goal is to go in the same direction and include other varieties such as Badini in Duhok, this region, as other dialects of Kurdish with less number of speakers such as Haurami, Zazaki, etc. And we have an initiative here in University of Duhok. We want to develop some tools and data sets for Badini also. If you are interested, you can contact me or Dr. Shahan to create a group if you are interested from Department of Kurdish Language, Department of English Language, and Computer Science. Our objective is to develop these technologies for Badini, which has a very specific situation because it uses the Arabic alphabets similar to Central Kurdish, but in terms of linguistic features, it's similar to other varieties of Northern Kurdish, and our goal is to extend this work to Badini also. Thank you.